So good morning, everybody. It is my greatest pleasure to meet you and welcome you here at ADG 2021. I hope you can hear me well. Predrag, can you hear me? Okay. So when I moved to Austria 10 years ago, I learned that Austrians are always on time. So that's why we start today on time, hopefully. And maybe some other people will join us. So it is a great pleasure for me that we are from 16 countries here and 56 people. But what is ADG? I think many of you are here in this community for several years already, and you know that ADG is a very successful series of conference. However, I'm not a member just for a couple of years, and it was beginning. I hope you can see my screen and you can read. Shall I increase the font size, or is it okay like this? It's okay. So it began in France in 1996 in Toulouse, and then in Beijing in China, in Zurich, Switzerland, also in Hagenberg in Austria. There was a conference 19 years ago, in Gainesville in France again, and Pontevedra in Spain, then in Shanghai in China, in Munich in Germany, in Edinburgh in the United Kingdom, and then in Coimbra in Portugal in 2014, in Strasbourg 2016, and then 3 years ago in Nanning in China. So we had to skip 1 year because of the pandemic. And unfortunately, this year we need to do and organize the conference online, but we hope that you will still enjoy this conference. And well, my first task is to say thanks to the organizers, the people who helped to put together this conference. First of all, the RISC Institute, the Research Institute for Symbolic Computation in Hagenberg, Austria. They couldn't host this conference in presence, but they gave us a lot of help. For example, the website is hosted at RISC, and also their knowledge in conference organization was very helpful. So thank RISC. On the other hand, we also have some sponsors. The JKU helped us. The JKU is the local university in Linz, Austria, to set up this conference via Zoom meeting, and also the DK Computational Mathematics, the doctorate program. They helped us financially. However, we didn't really use this financial help, maybe later. Well, I have to say thanks to our invited speakers, and very soon we will start with the program. So let me welcome Professor Davec from France, Professor Husti from Austria, and also Professor Kuchan from the local university, actually from the Austrian Academy of Sciences, Professor Quaresma from Portugal, and also Professor Windsteiger from RISC. So this is my welcome message to you, and let me give the word to Professor Janicic, who is the general program chair. Thank you.
Thank you, Zoltan. Thank you very much. Good morning to everyone, or rather, good evening to those of you who are in Japan, China, or United States. Welcome from my side too to the ADG 2021. It's been a great honor and privilege to me to serve as a program committee chair for this conference, and I'm very happy to be here now. I'm also sorry that we are not having this meeting in person. But despite these circumstances, this ADG has excellent program, and I'm sure that we will all enjoy it, and we are looking forward to hear all the talks. First of all, I also want to thank our invited speakers for accepting our invitation. As invited speakers, as Zoltan said, we have 5 leading experts working in the area of automated reasoning in geometry or in related fields. I also want to thank all the authors of submitted papers. We have 14 papers accepted, a high quality program spanning almost complete scope of the ADG. Finally, I want to thank all the session chairs for the following 3 days and all the people that helped and institutions that helped in organization of this event. This year, ADG has 2 innovations. One innovation is a focus topic, a topic that is in the scope of ADG or close to it. This year, we have decided it to be robotics. And we will have some invited talks in this field, but we will also have an open discussion session on Friday morning, in which we should discuss and brainstorm together about possible links and possible research challenges in links between automated reasoning in geometry and robotics, but also with some other research fields. The second innovation this year is the first competition of geometry provers, something that other sorts of provers already have for some time. And I'm sure it will be very interesting and that we will enjoy following the results and outcome of this competition. Now, I think we are ready for our first invited talk. It is my great pleasure to announce Professor Manfred Hösti and to thank him once again for accepting our invitation and for joining us today. Professor Manfred Hösti, during his career, worked at the University of Leuven, McGill University, and the University of Innsbruck. He has published more than 100 papers and books, and his research areas are in different sub-areas of geometry. But what is especially interesting for us and what is especially important for us is that he is one of leading experts in robot kinematics. And I believe we will hear something in that from that area today. And once again, I thank Professor Hösti for being with us today. We are very happy to have him today with us. Professor Hösti, please take the stage.
Okay, let me try to share my screen. Okay. Okay, that should work. Thank you very much for inviting me to this lecture. I have to confess that I was not very sure what I should bring in this lecture, but I thought maybe I can give you a short overview of the work I was doing in the last years. And I decided to talk about robot kinematics and the algebraic point of view. This would be an overview of my talk. I would like to give you a short introduction. Then I will go to explain a little bit the mathematical framework we are using. And then I come to the most important part, which is called constraint manifold and constraint equations. And I think this fits very well within the topic of this session of the conference. I have decided to use a relatively simple manipulator to show you all the things which can be done with constraint manifolds. I called it a paradigmatic case. Then I will go to some other examples which we have done over the last years, just to explain how everything can be transformed from the planar case into the spatial case, and where you can analyze and synthesize some devices which are already out in industry. If I have some time, I will maybe mention a few open problems, but I have to confess this is a very subjective point of view. These are problems, I think, which might be interesting in the future. As you have seen in my abstract, there are, of course, many, many different types of robots. So we can discuss a wide field of different devices. On the top line, you see what many people would consider to be a robot, which is a serial robot, industrial robots, as you can see. But there are other devices which have become important in the last years. Like you can see in the lower part here, this is a wire robot. These are parallel robots which are used for flight simulator training, for telescopes, and also as sensors. Other devices, as you can see here, you have mixed devices, a serial robot combined with a wire robot. This device is very interesting, has been introduced recently. It's a robot which has a high ability of sensing, and this tells me already where the robotics will go, into collaborative human and robot working, and these robots get a lot of feeling in their hands and also on the robot itself. Rolling robots, human robots, and rolling serial robots, just a few devices to give you an idea how wide this field is nowadays. When you look at the handbook of robotics, then you can see even more how big this field has become. This lists the main chapters of the book, which has about 1,700 pages. Robotics foundations, different robot structures. Then a very important part, sensing and perception, manipulation and interfaces, gripping, mobile and distributed robotics, swarm robotics, for example, a set of drones acting together, field and service robotics. In this part, you have the classical industrial robotics, space robots, medical robotics, rehabilitation, and many, many more. The last chapter is human-centered and lifelike robotics. Here you have bio-inspired robotics, for example. Human-centered means now humans and robots get interact together, they work together. And there you have the important fields, security and safety. Security means that the robot does not any harm to the human being working with him. Security means in this case that the robot software is also secure, that no hacker can go into this. Just imagine you have a workplace with maybe 100 or 1,000 robots, and the hacker breaks in, and the damage that could be done is incredible. So I have to limit myself. My work is essentially in a field which is called computational kinematics. Computational kinematics, we are doing intense computations of numerical, but also of symbolic, and also is maybe no longer correct. This is a citation by Jorge Angeles from 1993. And I would say more and more of symbolic nature. What are we doing in computational kinematics? We want to answer questions using, with respect to the analysis or to the synthesis of kinematic chains. And kinematic chains themselves, these are the basic elements of any robot. These are rigid bodies connected via joints in different kinds of devices, serial, parallel robots, wired, humanoids, and so on. And the fundamental questions we want to answer are questions respecting or with respect to forward inverse kinematics. Forward kinematics means you know the device and you know the joint angles or the joint parameters in the device, and you want to know where the robot is. inverse kinematics, you know where the robot is, and you want to know what are the joint angles you have to feed the controller so that the robot goes into that pose. Singulars solutions are very important because there the systems become unstable. And of course, we want also to know what is the size of a workspace, what can the robot do, or the synthesis questions that mean synthesis. You want to design a robot or a mechanical device that should perform a certain task. This is synthesis. Mathematically, these problems can often be described by systems of multivariate algebraic or functional equations. It turns out that even relatively simple problems involving such systems turn out to be very, very complicated. Of course, the whole field is governed by nonlinear equations. Some geometric insight and some geometric pre-processing is very often the key to solution. And this is the case why some of my students and doctoral students were very successful, because they applied a lot of geometric insight. Okay, the mathematical description of such a device essentially needs two ingredients. First of all, you have to make a decision which parametrization of the Euclidean displacement group you want to use. And the second decision is which mathematical description of the mechanical device you want to use. Let me make a bit more precise. You could use either Euler-Engels Rodriguez parameters. These were the parameters which were very widely used at the beginning of robotics, but then people have realized those parametrizations contain parametrization singularities, so they have switched nowadays to Euler parameters or Studi parameters, which are essentially quaternions or dual quaternions. So in modern controllers of robots, the parametrization is mostly done by quaternions. The mechanical device itself is generally, most of the time, I have to confess, described by vector loop equations. But on the other hand, what I will talk today mostly, you can use implicit constraint equations. In our opinion, these constraint equations describe the systems better because we are much interested in a global description of the mechanical device. It means we want to know how the manipulator behaves in his global workspace, anywhere where it can go with any orientation. Therefore, we have decided to use Studi parametrization or dual quaternions as to be able to use powerful tools from algebraic geometry. And of course, this is also linked to a multidimensional representation of the Euclidean displacements. Very briefly, the mathematics looks like this. We are using the so-called kinematic mapping, and the kinematic mapping does essentially a map which assigns to an element of the Euclidean displacement group in three-dimensional space a point in seven-dimensional space. So essentially there we have 8 homogeneous coordinates, and when you map back to Euclidean space, these coordinates find entry in transformation matrices, which are parametricized now with the so-called dual quaternion coordinates or kinematic mapping coordinates. These are 4 x's and 4 y's, and these coordinates are linked by a quadratic equation. This equation is called a Studi quadric, and the coordinates are called the Studi parameters, and they are essentially dual quaternions. I do not want to go into detail with this, but I want to show you how we are using these things. And the most important notion is the notion of constraint manifold or constraint equation. A constraint manifold now consists of all poses and end effector of a mechanism or a robotic mechanical device can attain under the presence of some mechanical constraints. Mechanical constraints limit the motion. It's like in your arm. When you think with your hand, you can move in three-dimensional space with any orientation. But of course, the motion of your hand is linked by the length of your forearm, by the length of your fingers, and so on. This is meant by mechanical constraints. The sequence of the links in such a chain corresponds now mathematically to a sequence of coordinate transformations. And this sequence determines the constraint manifold mathematically. The mathematical description itself is done now by constraint equations. If you are interested in more detail, I have recently written an entry in the Encyclopedia of Robotics concerning the constraint manifolds. There are a little bit more detail. But I want to explain this concept with some examples. When you have the constraint equations, with implicit constraint equations, you can get global information on the forward kinematics, meaning where is the end effector when the joint angles are given. The inverse kinematics means what are the joint angles when the end effector pose is given. Then, of course, the forward singularities, which means an instability of the end effector of the robot. The inverse singularities, they mean an instability of the legs of the manipulator in the kinematic chain. You can get global information on input-output relations, and you can also get information on a possible synthesis. You want to design a manipulator to perform a desired task. I have decided to take a very simple example. This is the device which I want to discuss and to show you all these mathematics which is linked. It looks very simple. It's a planar device. Here you have a base. On the base you have legs, as we say, which are the arms of this manipulator. And you have 3 such arms. And here you have an end effector. And this end effector is geometrically manifested by a triangle. So essentially you have to think of in the 3 points P1, P2, and P3, you have the motor, and these motors move this device, and we can show that it can move within a certain workspace in any orientation and translation that you can think of. So now the first question is forward kinematics. I will explain it geometrically. Forward kinematics mean that the angles alpha, beta, and gamma are given. So it means the first parts, as you can see, the upper arm of that arm, moving arm, they are fixed. Here you have in the point J, you can think of this is an elbow joint, and when you look at the end point of the elbow joint, this point P1, little p1, essentially it's constrained to move on this circle. Yeah, it cannot move anywhere else. So you have 3 such things. So the forward kinematics in geometric point of view can be formulated in the following way. You have 3 circles and you have a triangle with given points P1, P2, and P3. And the question is, how can you place this triangle on the 3 circles? It seems to be a very simple task, but essentially this is nonlinear, and it has been proven that you can have up to 6 real solutions of this problem. So given the inputs, you can have 6 poses of the end effector. Mathematically, this constraint is formulated in this constraint equation. This is a completely general constraint equations. The ingredients in this constraint equations are the x0, x3, y2, and y1. These are the pose coordinates. And then you have the design coordinates, and the design coordinates are these little x and this little y. The m's are the centers of the elbow joint, as you can see. As the elbow joint can move now, you can parameterize the m and the n. via a circle constraint. This is this parameter u, and this parameter u essentially is the algebraic value of the input angle. So this is in the forward kinematics, this u is given. You have three such equations and you have to solve the equations. To make it a little bit simpler, I have decided to assign some parameters, some design variables. They are listed here. Then you would have a set of these three equations, and it turns out you can eliminate now. And I want to emphasize, there is no need to do a design variable decision. You can solve the system completely general. You will arrive at the polynomial of degree 6 at the end, and the polynomial of degree 6, of course, has to be solved numerically. Back substitution will give you the solution. Here you see one solution of this, and essentially what you get is the position of the origin of the moving system and the rotation angle of the system, and you would get 6 of them. Inverse kinematics is vice versa. You assign in the same set of equations now values to the pose parameters, which are the x with subscript and the y's with subscript, and you want to know the input angles, the u's. This is, of course, a much simpler task, and you see these are three quadratic equations which can be separately solved. This is nothing special, but for the kinematics it is special because what you get is all those solutions. This is the given end effector pose, and of course geometrically this problem is very simple. It means the intersection of two circles, because then you have to find the elbow joint, and you see each of them has two solutions, but they can be combined arbitrarily. So you have essentially, as we say in robotics, 8 different working modes. And these different working modes are separated by input singularities. And an input singularities you can even see with your hand. When you are in a stretched out position, you are in an input singularity. You cannot move out further. And the two solutions with anatomy I cannot show. You have an elbow up and an elbow down solution. And this bone here in our arm doesn't allow us to go through a singularity. And this is maybe nature has made a wise decision, but the robot can do it. Singularities means, I have shown you already, a singularity shows either the end of your workspace, or it shows a dangerous situation within the workspace. We have two types of singularities. The input singularity I have already shown you. This is the stretched out arm. When you have a system, you have this system of the three constraint equations. Because the pose parameters are homogeneous, you have to add a normalization condition. This one here added is essentially the classical sine square plus cosine square equals 1 condition, which was added here. And you differentiate the system, you would arrive at an equation of this type, where you have two matrices. One matrix is the Jacobian matrix of the forward map, and the other one is the Jacobian matrix of the inverse map. As you can see, this Jacobian matrix of the inverse map is something very, very simple in this case, but I have to tell you, in other devices, this can be quite complicated. So when you want to solve this system, then you will already see that it is algebraically quite involved. In the forward singularity, you will see an infinitesimal local motion even when all inputs are locked. It means you know the joint angles of the device, the alpha, beta, and gamma in our device, and you want to know where the end effector is. When you arrive in a singularity, meaning that the determinant of the forward Jacobian matrix vanishes, there is a linear dependency then within the pose parameters. You arrive at a system of 5 equations, and these 5 equations contain pose parameters and also input parameters. So you can decide now where you want to get the singularity set. You can decide either to have it in the pose space or in the input space. This depends very much on the task you want to perform. I have shown it here now in the pose space. That means you have to eliminate from this set of 5 equations the input parameters. And when you do this, you get something in pose space. This pose space now is a 3-dimensional projective space. So you can even show what is the result. You will arrive at a surface. And in this case, the surface is of a high degree 44. Just a slice of this surface is shown here in this figure. And you can see this is already highly complicated. By the way, this surface is so complicated because we cannot distinguish between the working modes in this picture. And it is an open question if it is possible to find the singularities in a specific working mode of the manipulator. Just to show you the result, what is the meaning here? This is computed one of the points of these surfaces, mapped it back into the Euclidean space. This is a singular configuration. Note that the end effector is now below the fixed platform. And the meaning is that lines which are on the forearm of the manipulator, here on this blue is the line G1. On the red, K2 is the line H1. And the blue one, the third leg is F1. They intersect in one point. And here in this point, you have an infinitesimal rotation center, and the manipulator is shaky. In a specific task, you do not want to get into such a thing. The inverse singularities are much simpler because of the structure of the Jacobian input singularity matrix. You can split it into 3 parts. I have just discussed the third part. And when you eliminate the input parameters, now you want to see the input singularities in the pose space. Then this equation splits into 2 terms, and the 2 terms have a simple geometric meaning. Each of them is a hyperboloid. And when you are on a point of this hyperboloid, the manipulator will be in an end effector pose where at least one of the legs is stretched. And you can show here, when you are on this hyperboloid, you will be in a stretched position, as you can see here. When you are on the other hyperboloid, you will be in a folded position. So the legs are in a folded position, and in between you have a valid workspace of the manipulator. So this is also a workspace analysis, so you can show where the manipulator can safely be. Of course, such a stretched position is a position where the manipulator can go from one working mode into the other one. When you eliminate the pose parameters, then it becomes even more complicated. Then you will arrive in the projective space of the poses at the surface of degree 28. And you could again do a forward map, and you could compute, and one of the poses would be singular. Let's go to 3. There is also one more thing what you can prove. One would think that 2 poses in the direct kinematics must be separated by a singularity, just as I have shown by my stretching of the arm, which means one solution and the other solution, they are separated. But it has been proven that for such a parallel manipulator, you can link 2 solutions. Each of those points here is a solution of the direct kinematics with a path going through a hole, and it's proven that this surface has enough holes so yet that you can always link 3 of the solutions. Meaning, when you want to go from a solution of one kind to a solution of another kind, then the determinant of the Jacobian matrix would have different signs. So you would have to cross the singularity surface, which is of course a zero of that path. Let's go to space. I just want to show you a simple example, which is known since very, very long time. This is the Schatz mechanism and Precast overconstraint 6R chain. As I can see that Josef is also among us, they have done a lot of work with this overconstrained 6R chains. But I want to show you here something else. I want to show the methods we are using that it's maybe more interesting. This chain has very special design parameters. They are listed here. But the important equation is this alternates a sum of squares of the distances between the rotation axis in this 6R device. You can write in a very simple way the constraint equations of this 6R chain. These constraint equations, this has turned out by the PhD thesis of Martin Pfurner, who is also among the audience, as I have seen, that it is parameterized via V1, which is the input parameter, and V6. You can compute the Hilbert dimension, and the Hilbert dimension of this set of equations is 1. Kinematically, this tells us that the 6R chain, which according to the classical theory should be rigid, has a 1 degree of freedom. And using Gröbner basis with a total degree ordering and putting the input and the output angle at the end of the ordering, you can even arrive at the input-output equation of this mechanism. This means when you have a motor sitting at the first joint, you can know via this equation how the output joint, meaning the last angle, would perform. This is part of Martin Pfurner's thesis, and you can download the thesis if you wish. There's also an overview paper by me and Dominic Walter, former PhD student, recently. I want to show you another device, which is a spatial parallel manipulator, so-called 3RPS. It's a manipulator which has a revolute joint here, a prismatic joint to elongate these lengths, and a spherical joint here, and you have 3 of them. This has been done in Josef Stadelbauer's thesis, but this device now has been performed in a medical device, and this medical device will be used, this is a prototype, will be used for ankle rehabilitation, and the controller of this device is completely using this set of equations. This set of equations does everything for this manipulator. So you have 6 equations. You can see 3 of them are very, very simple. They say essentially that the spherical joints of this manipulator can only move in a plane. Let me go on to the inverse kinematics of a serial 6R manipulator. I have to be fast, as I can see. Here you can see what I mean by the forward kinematics of a kinematic chain. The M matrices are the rotation matrix about the axis of the manipulator, and the G matrices perform a transformation of the coordinate system to the next revolute joint. Then you have again a rotation matrix, coordinate transformation matrix. When you multiply them together, you get the matrix A, and this matrix A essentially tells you how the transformation from the end effector to the base coordinate system works. When you want to solve the inverse kinematics, you know this matrix A, and you want to know what are the inputs in the M matrices. So what we do is we split up into 2 chains, and we say essentially inverse kinematics means a handshake. So we want that the left and the right come together, and this is everything what is needed. So you have a system of equations, and it is very old result that this system has 16 solutions. But algebraically interesting is the question, can all 16 solutions be real of this system? And this has been shown. Here is an example taken out of the thesis of Matthias Brandstätter. Here you can see a manipulator which goes in 16 different poses to the same pose of the end effector. Let me finish off with another system which is very interesting. These are wire robots. In most stadiums today, and even at the Olympics, you could have seen that there are so-called SkyCams. The SkyCams are wire robots. Essentially for the SkyCam, because you don't need the orientation, 3 wires would be enough. Most of the time, the people also take a 4th wire, which is hidden here a little bit. This is not only because of redundancy, because of the problem that wires can only pull and not push. Geometrically, it is shown here on the right side. You have 3, and I show you for 3 strings, and you have 3 strings. You have a rigid body, and you have a center of gravity. The body itself is not shown. I just show the center of gravity. You have 4 lines, and the forward kinematics solution, the direct kinematics solution, is a very, very complicated problem. When you are working with 2 cables, then you are in the planar case. You have either 12 or 24 solutions. 24 solutions when you allow that you flip your end effector over. In the case of 3, you have 156 solutions over C. So this is a very complicated problem. And I have to say already, this is an unsolved problem. First of all, how many solutions are possible? Second of all, how many solutions are feasible? Because this number 156 gives you also solutions which are above the base, yeah, because the solutions, they take just distance equations and equilibrium conditions, which means essentially, which means essentially the following. I will explain it very briefly here with this planar device. The planar device here is in a stable solution, but it is of course, not a solution which it is in an unstable equilibrium to be correctly. But here the solution is quite simple. When you think of that you have here rigid rods and revolute joints in A, B, C, and D, then the point G can move on a so-called coupler curve, and the equilibrium solutions are in points where you have a horizontal tangent. So this is very well known how many you can have. You can ask, for example, what is the class of this sextic curve? And it's very well known that the class is 12. So you have 12 solutions and the system is proven. But you can also have solutions which are here above. And so the number 12 is for sure not correct. There is a conjecture that maybe only 6 of them are possible as feasible solution. But then you can have a surprising result. And the surprising result is here on the right side down. You can have a cusp, and the manipulator can fall into this cusp, and there is by far no horizontal tangent of this, but this of course a singularity, and this also counts. At the end, maybe 5 open problems. First question for me is, can dynamics also be formulated within this algebraic framework? So can you use this algebraic parameterization also to do the dynamics? My opinion is the question can be answered with yes, but it needs a lot of work. Second of all, complete solution of planar and spatial wire robots. So do we have a chance to filter out the non-feasible solutions? But this means for you going into semi-algebraic sets, and semi-algebraic sets because you have inequalities. The forces have to be greater than 0, and you should not go into the negative forces. Yeah. Multiplicity of solutions. It means, can solutions of the direct kinematics merge? Yeah. In the planar case, I can show all 6 can merge. And this means a high shakiness of the manipulator. but with spatial robots, nothing is known at all. Moreover, global path planning of mobile robots. It means, can we transform our global kinematics also into the path planning of mobile robots? This is done, by the way, at the moment, just with local solutions. The over-constrained zigzag classification, Joseph, this will be your task. But there is also something new. This is under-constrained extreme NR linkages. It has been shown recently that we can have closed NR linkages, which we call Möbius linkages, which have only 1 degree of freedom when they are in extreme positions. So I finish. Thank you very much. I have taken a few minutes more. I apologize for this.
Thank you, Professor Hasti, very much. We can clap hands, so maybe the audience already found the way to clap hands for this excellent lecture. Yes, or more traditionally, we are very happy that we had this excellent lecture. And now, discussion, please. We already have some hands raised. You can raise your hand. I hope you found that option in the interface. You can raise your hand, or you can just turn on your microphone. It is you can do it yourself. So please, discussions and questions for our invited speaker. I think I saw one hand already.
Sorry, it's Pascal. I did not find my hand, sorry. So okay. Here it is. You mentioned elimination method in your talk associated with a numerical resolution. And I was wondering what elimination method you consider. Because there are several.
Yeah. If possible, we are trying it with Gröbner basis, Gröbner-based elimination, or otherwise we do simply elimination with Maple methods and discriminants and so on.
Discriminants, okay. Because there are some methods like regular chance, which compute the irreducible components. Do you think it is interesting or not?
Yes, it is interesting. We are also using numerical algebraic geometry, and maybe you know the work of Charles Wempler and the group in Notre Dame, and they are using these witness sets to separate the components. Yes, it is very important. I could have talked about this because different components can occur. I was thinking of showing one manipulator which where the workspace splits into total different components with different geometrical and kinematical behavior. So a manipulator can, for example, go into a component which can be separated. You find the ideal which describes this component, and then the manipulator can just perform in this component a spherical motion. And then it is interesting for us to find, is it possible that the components intersect in a point, in a curve, or in a higher dimensional manifold, so that it can switch from one component into the other one? So yes, it is a very important, and it's a very good question. Yeah.
Thank you very much.
More questions? Thomas?
That's a good question. We don't have a time anymore, I guess, no? So
we will have
quick.
Quick, yeah.
Yeah, okay.
Or I'll answer it on Friday, next week.
Okay, I'll just give you the question, and if you think you can answer it on Friday instead of now, just let me know. So, since I was not here for most of the time, the best question to ask is the question that I think, do you know anything about the real solutions?
Of what?
Number of real solutions.
Of what? Of the wire devices?
Of the wire, yeah.
No, nothing is known.
Okay,
nothing is known.
That was quick enough.
Yeah, there are examples where you have out of the 156 for the 3-box problem, as Paul would call it, where you have 28 real solutions, 30 real solutions, but it is the upper bound of real solutions is not known, and not even how many solutions are feasible. But as I have talked already before, this is a semi-algebraic question. Yeah. And you know, even simple semi-algebraic questions are difficult.
Yeah, I get it. Yeah, thanks.
One more quick question from Thomas, Professor Thomas Resio. Please, Thomas.
Yeah.
Yes. Hi, Manfred.
Hi.
Yes. So,
nice to see you.
Yes. So my quick question is about the role of all these mathematical approaches in industry. So industrial robots, how they benefit from all these mathematical problems? Okay. This is my question.
It's a very good question, because it is also part of the frustration I have sometimes. Because I have learned engineers very often are happy with one numerical solution of what they want. For example, let me make a very, very precise example. I have talked about the inverse kinematics of the industrial robots, the 6R manipulators. We could show that it makes a big difference with which starting position, with which solution of the inverse kinematics you start. But the engineers, what they do is they have a system of equations. Most of the time they take loop equations, they throw it into a numerical solver. When they find one solution, they are happy. Yeah. So the answer is, it would be desirable that they sometimes go back to the kinematics, to the dynamics, even dynamics, yeah, and study a little bit more, then they would get better performance of the robots. I can say this. We can show that in examples.
Thank you so much. Very interesting.
Thank you all. If there are more questions, if not, then let's thank our speaker again. Thank you very much.
Thank you for having me.
I hope we will still have opportunity for discussion, especially on Friday, when we will have this open discussion session, mostly on robotics. Thank you very much again. And now I give stage to our chair for this session, Professor Jose Cappo. He will take over. Thank you again.
Thank you. We have -3 minutes left. So the next speaker will be Christoph Kutjan. He is from, as far as I can remember, Austrian Academy of Science. And he's talking about realization of rigid graphs. Oh, okay, I'm involved in it, but maybe he's saying something surprised as well. So Christoph, you have the platform. I think you're muted, no? Should I unmute you? I think, yeah, now it's working.
Okay, and you see my full screen? Okay, so thank you very much for the invitation to talk at this conference. It's my pleasure to present this joint work with, as you already said, Jose Capco was involved, as well as many other members of the symbolic computation group at RICAM. This group is led by Josef Schicho, who is also here in the audience. and other members of or former members of this group, or no, actually all are current members, Matteo Gallet, Georg Grasecker, Niels Lubes, and also a colleague from INRIA in France, Elias Tsigaridas. And so in the previous talk, we have seen robots that are moving, and somehow I'm going to the opposite. I want to talk about rigidity. So let us try to approach this topic in a gentle way with a very simple example. So we look at a graph G with a set of vertices and a set of edges, and we consider a map from the set of edges to the positive real numbers that we understand as the given prescribed length of these edges. We want to assume that this graph, together with this labeling, is realizable. That means there exists an embedding of the vertices of the graph in R2, such that the lengths of the edges agree with the given labeling. So here's an example. We have a graph with 4 vertices and 4 edges, and we have given this labeling here. And one possible realization of this graph is shown here. So now we want to talk about rigidity. So is this graph rigid? Obviously not. We can move it in a smooth way. But if we add another edge into it, like this one, and we also prescribe a length for this edge, then obviously this somehow in an intuitive way, this construction here is rigid. So our first attempt at a definition could be that we call a graph G rigid if there is exactly one way, modulo, of course, I can move or rotate this whole figure, how I can embed it into the real plane. But this definition is not good, because if we look at this example, there is not exactly one way, but as we can see on this picture, there's also a second way how we can embed it. But in contrast to the previous figure where we had only 4 edges, we do not have infinitely many. So in this smooth motion, we had infinitely many embeddings. And so our second attempt at a definition could be, we say there are only finitely many ways to embed the graph in the plane. Okay, but still this definition is flawed for the following reason. Let's look at this graph. That's the so-called 3-prism graph. And if we say that this graph, we want to call it rigid if there are only finitely many ways, then we see obviously that this graph, according to this definition, would not be rigid, because we can rotate the upper triangle around the lower and we get again infinitely many embeddings. However, this is just the reason for this behavior is just because we have this very special embedding. If we now choose a different labeling, different edge lengths, for example, this one, so we just flip this upper triangle, we have different edge lengths, then it turns out that this graph is indeed rigid. That means now we have only finitely many ways to draw this graph. Here's another possibility, so we can flip this or symmetrically like this, but there's no smooth motion possible here. Okay, so our final definition of rigidity is that for a generic edge labeling, we want to have that there are only finitely many embeddings. So generic is like a random choice of these parameters. So we call such graphs minimally rigid or Laman graphs. And the property is that if we remove a single edge, that graph will be non-rigid. That's why they are called minimally rigid. So now about a characterization of rigidity. How can we classify minimally rigid graphs? If we make a quick calculation and compare constraints and degrees of freedom, then it's clear that we have that we have 2 times the number of vertices unknowns. These are the coordinates. Each edge gives us 1 equation, and we want to mod out the translations and the rotations. So we have here the dimension of the group of direct isometries, which is 3. So we should have, in order to have only finitely many solutions, we should have this inequality that the number of equations must be at least 2 times v minus 3. And actually, there is a theorem that was first proven by Hilde Geiringer and then independently later by Gerard Laman. This is a bit unfortunate that Geiringer's work got somehow forgotten for a long time, and that's why in this field many things are named after Laman. Also, the results date back to the 1920s by Hilde Geiringer. So the characterization is that a graph is minimally rigid if and only if we have here equality. The number of edges is equal to twice the number of vertices minus 3. And there is a second condition that must be satisfied for any subgraph. So if we have a subgraph G prime with vertex set V prime and edge set E prime, then we must have this inequality. So that is, so maybe you are surprised that the inequality is in a different direction, but so we have to think that in no subgraph we have too many edges. This must be avoided, because if there were too many edges, then this implies that in some other part edges are missing. Okay, so let us look at some examples. If we look at graphs with 2 vertices, there's just a single minimally rigid graph that is shown here. If we have 3 vertices, then also there's just a single graph that is a triangle. Similarly, if it's 4 vertices, we get these 2 triangles that share an edge. But if we increase to 5 vertices, we find that there are 3 different minimally rigid graphs. Okay, and then if we continue this search with 6 vertices, we get here 13 graphs. And here you see all the minimally rigid graphs with 7 vertices. There are 70 of them. Okay, so one game you can play with this is that you enumerate all these minimally rigid graphs. So we have seen these numbers on the examples. We can go to the online encyclopedia of integer sequences, an extremely useful tool if you're working in combinatorics, if you want to know something about a sequence of numbers that you encountered in your work, whether it's related to some known concept. So we did this, we found this entry, and this is an old screenshot how the encyclopedia looked like some time ago. And it predicted the next number to be 609. Then we calculated it and we got 608. And so after a lot of checks, we convinced ourselves that our result was correct. And we found the mistake that people did when calculating this number. So we corrected the entry and now it's shown correctly. And we also calculated more of these numbers. So you see when you have 12 vertices, there are already something like 44 million such graphs. So the enumeration is extremely difficult because there's no really efficient way to do that. And then later, some other people, they wrote an obviously very efficient C program for this enumeration, and they got a few more numbers, and this is the current state of the art. But actually, we are not so much interested in the number of graphs, but we are interested in the number of realizations. Recall that we defined a minimally rigid graph to be one that has only finitely many realizations. And a natural question, of course, is how many are there? So if we look at the only minimally rigid graph with 3 vertices, that is the triangle, how many realizations does this graph have if we do not consider rotations or translations? We get 2 because we we consider the reflection as two different realizations. But that's it. Now, if we go to the next case, the only minimally rigid graph is 4 vertices. Recall, these are the two triangles that are attached to each other. Then we get more realizations because each of the two triangles we can flip. So we get 4 realizations. And so if we continue this game, if we build a graph that consists of triangles that are attached to each other, such graphs we will call H1 graphs, then it is very easy to determine all the possible embeddings, because basically for each triangle you have 2 possibilities. So you get in total a power of 2 as the number of realizations. So these are the so-called H1 graphs that are constructed by starting from a triangle, let's say, and then you add 1 vertex and you connect it with 2 existing vertices, and you repeat this procedure until you have your graph. And yeah, so here, this is the explanation how you see the number of embeddings, and you find that this is this power of 2 to the number of vertices minus 2 number of realizations. So this is very obvious. And so let me give this definition. For a minimally rigid graph, G, we say, we call lam G, the Laman number of this graph, the number of realizations for a generic realizable labeling. Or later we will turn to a complex setting, then this realizability is not anymore relevant. So now if we turn to the more complicated case where we have graphs that cannot be constructed in this very simple way, that do not have this H1 property, then we could compute this number of embeddings as the number of solutions of a system of equations. So if we denote by xv, yv, the coordinates of the vertex v, and then for each edge uv that connects the vertices uv, we have this quadratic equation where lambda uv is the length, the prescribed length of this edge, this labeling. Okay, and as I already mentioned, from now on we will work over the complex numbers for several reasons. This makes our work much more easier, and working over the complex numbers means that we, instead of positive real numbers for the edge lengths, we allow complex numbers, and also for the locations of the vertices, we allow tuples, pairs of complex numbers. So our embedding is now in C2. Okay, so if we look at this 3-prism graph, then by just writing down for all these 9 edges, we get these 9 equations. And now we have to take care of translations and rotations. So we can take care of translations by fixing one point. Let's say we fix the first vertex to the origin. So x1 and y1 are both 0, so they disappear here. And to take care of the rotations, let's say we claim that this vertex number 2 is on the x-axis, or on the, actually here it's on the y-axis, so the coordinate x2 is 0 and y2 is on the positive y-axis. Okay, and then these equations simplify even more. And the question now is, how many solutions does the system have? Of course, the most natural thing is to do Gröbner basis, but even for this very small system, this is not feasible if you keep these parameters. Recall that we want to talk about generic labelings. so we should keep them symbolic, actually, then this is not feasible with these 9 parameters. So what we can do is we replace these parameters by random numbers and accept that the result may not be completely rigorous. So if we compute the Gröbner basis for this simple system, this is the output. So to fit it on this slide, I have to make the font so small that you can see nothing. The only thing that you may see is that there are quite long numbers involved. So next natural thing to do is to do this modulo prime number. Then the thing gets a little bit smaller so that we can see something. And since we are non-rigorous anyway, it doesn't matter. Now, from the Gröbner basis, we should look at the leading monomials here in red. And from this, we can read off the number of solutions. So here again, these are all the leading monomials of this Gröbner basis. And if we look at all irreducible monomials, they are listed here. So they are under this staircase of the Gröbner basis. We see that there are 24 such monomials. So we get 24 complex solutions of our system. And this is the number of embeddings of this 3-prism graph. Okay, so now if you look at all the minimally rigid graphs with 6 vertices, then almost all of them have the same Lamarck number, 16. That is this power of 2 that we expect if we look, for example, at this graph that is composed of triangles. So we expect 2 to the 4. And there's only one graph, that is this 3-prism graph that we have just looked at, that has a different Lamarck number, namely 24. Okay, so now the main result of our work is an alternative way to compute these Lamarck numbers, this embedding number. And so the basic idea, the approach that we take is to consider a certain map and to interpret the Lamarck number as the degree of this map. So recall we have these quadratic equations that we consider. And if we now take this expression on the left-hand side to define a map, so we take as input all the coordinates of all the vertices and map them to their sum of squares of these differences. Then if we have an embedding that is consistent with the given labels, then as the image of this map, we should obtain this lambda uv square for each edge. So if we now, for the moment, ignore these translations and rotations, then that means that here these guys are hit as many times as there are realizations of this graph. So now, in order to apply algebraic geometry, we want to work in projective space. And for this reason, this map FG should be a homogeneous map. So what we do is a change of variables. So we have here, this is the expression that defines our map. We factorize it over the complex numbers, since we are now anyway working over the complex numbers. We sort these summands here in a different way, and we replace them by the new coordinates, by new variables. And then our equation here becomes very simple, and in particular homogeneous with respect to the x variables and with respect to the y variables. Okay, now how to handle these translations and rotations. As we said, we move one vertex to the origin, we fix the position of another vertex, and we fix the length of one edge. So to write this down, I define the number comp G, or the set comp G, the set of connected components of a graph. So you may ask, why do I consider connected components? Because we have a graph that, if we want to talk about rigidity, obviously has to be connected. This we will need later when we consider B graphs that are not necessarily connected. So for the moment, so for the moment, this is not so important. We define this vector space that whose dimension agrees with the number of connected components. So for the moment, this is just one. It's a one-dimensional vector space. And actually, it's generated by the vector that has all ones, because everything is one in a single connected component. And so using this setting, we can compute the number of realizations of a given graph as the degree of the following map. So you see the result of this map is this expression that we had on the previous slide. And now here this gets a little bit complicated, but this is just because we want to deal with these conditions here. So if I color them, you see that here modding out with this vector space of dimension 1, this has the effect that one vertex is moved to the origin. Then somehow by using a projective space here, we kind of fix another vertex, at least along a line. And then here we fix the length of a single edge to compensate with this positioning of the other vertex. Okay, and so what is still disturbs us a bit is that we have here this coupling of the x coordinates and the y coordinates. This somehow prevents us from continuing. So to have a way to separate these two, we introduced the concept of a B-graph. So a B-graph is just a pair of graphs. And now we allow that these graphs have need not be connected. They can consist of several components. We allow multiple edges that we didn't allow before for obvious reasons. And we allow self-loops in the graph. And so these two graphs, G and H, they have their set of vertices, but they share the same set of edges. So this is just a notational trick to say that there is a bijection between the edges of the graph G and the edges of the graph H. So we identify them in a one-to-one way, and therefore we call this set of edges, we call them B edges, because somehow they appear in both graphs. And so now we do a similar thing, we define a similar map now for B graphs. So the difference is here that the x coordinates, they are taken in the first graph, and the y coordinates, they are attached to the second graph. And so instead of xu, xv, and yu and yv, we have now different things. And so we have decoupled them. And this B edge means that, the indices UV, they form an edge in the first graph, and TW, they form an edge in the second graph. And we define the Laman number of such a B graph to be the degree of this map. And we can actually show that the Laman number of the original graph G that we want to compute is the same as the Laman number of the B graph that is obtained by duplicating the graph G. Okay, so now you see this already gets quite technical, and I don't want to overwhelm you with too many technicalities. So now I just give a very rough outline of how this strategy continues. So far we have worked over the complex numbers. We introduce now a new parameter S, and consider the solutions of our system involving this parameter S. They are algebraic solutions, so we can represent them as Puiseux series. And instead of studying the pre-image of the distances that we have given, we perturb these distances by powers of this parameter S. And the powers are given by a certain weight vector. So we have rational powers here of this variable S. And then afterwards, we apply a tropicalization. So we look at the valuation that is the smallest exponent that appears in such a Puiseux series of these x and y coordinates. in the pre-image of this perturbed point. And this pair of valuations, we call this a B distance. So this somehow corresponds to the distances between the vertices in our original setting, but now in this perturbed setting with the valuation, it's a bit different, but still we call it a B distance. And so if we choose an arbitrary, a random, a general weight vector here, then we can show that actually all these B distances are different. So computing our number is nothing else than enumerating all these B distances. This is a difficult problem, and we can make it simpler by choosing a very special weight vector, namely all exponents to be 1. In this case, we can show that these B distance only takes the values 0 and 1. So in particular, there is an easy way to enumerate them. We just have to consider all 0, 1 vectors, but we lose this property that of uniqueness. So what we get is that the pre-image is partitioned with respect to this B distance. So if D is a B distance, we get several solutions and we have to add them up. And we get a recursion as to compute our Lamarck number as the sum of Lamarck numbers of simpler graphs. Good. Yeah, actually here I want to jump over certain technical details. And so to state this recursion, this is our main result. We need 2 operations on graphs. One operation is the graph complement. That just means that we have a graph, we have a subset of the edges, and the complement is just removing these edges. So if we take as an example this simple graph, we color in red the edge set E prime, then the complement is just with these edges omitted. The second operation is the graph quotient. We denote by the slash. And this works as follows. Let's look at the example. Again, we have this graph. We choose this subset of edges. Now we look at the connected components that are induced by this subset of edges. They are indicated here. And for all these connected components, the vertex, all these vertices are condensed into a single vertex. And the red edges, they are removed and the other red edges remain. So if you identify all these 3 points, then the only edge that survives is this one, and this gives here this loop. So we had B graphs, and for B graphs, these operations work as follows. So we always do one operation on the first graph and the other operation on the other graph, or vice versa. So if we have here, if we look at this B graph, we choose this edge set, this subset of the B edges. So now it has to be understood, this is not shown in this picture, that let's say this edge is identified with this one, and this edge is identified with this one, for example. And so now if we do the first operation, that means we do the graph quotient here and the complement here. And if we do the other operation, then we do the complement here, we remove the 2 red edges, and we do the quotient here, we get this graph. And so finally, this allows us to state the main theorem, that is a recursive combinatorial formula for computing the Lamarck number of a B graph, and therefore also of a graph. So you see that here we compute the Lamarck numbers of 2 simpler graphs. And then here we have the big part of the recursion. We have to sum over all the partitions of the B edge set into 2 subsets according to certain conditions. And we have to compute the Lamarck numbers of the 2 simpler graphs that we get here. So this algorithm is, of course, far from being efficient, because here we have basically 2 to the something, an exponential number of possibilities, but still it is much, much faster than the Gröbner basis approach. So here are some technical conditions, the initial conditions where to stop this recursion, but basically that's it. And so now we can use this to compute actual numbers. So for this one, we get 24, this we already knew. This is, so now we look at all the minimally rigid graphs on a certain number of vertices. And since now this runs relatively efficient, we can compute all the Lamarck numbers, and we can look which one is the graph which has the highest Lamarck number. And so they are shown here. With 8 vertices, we can get 136 realizations, 9 vertices, 10 vertices, 11, 12 vertices. So recall this was the highest n where at that time we had the full enumeration. So computing this number means computing the Lamarck numbers of 44 million graphs. And that was clearly how far we could go. And so for higher numbers, we just experimentally try to identify graphs with very high numbers of embeddings, but we cannot claim that this is the highest. So for example, with 18 vertices, we find this graph, and it has almost 2 million different realizations over the complex numbers. Okay, and using these results, we can now obtain lower bounds for this maximal number of embeddings. And for this purpose, there are 2 constructions. Let me show you the first construction, the so-called caterpillar construction. So we start with a minimally rigid graph. In this example, we have this 3-prism graph, and then we place k copies of this graph in a way that each 2 copies share an edge. So what we get is a graph that has 2 vertices plus 4 times k in this case, or generally v minus 2 vertices, and this number of edges. You can easily calculate that the condition that this graph is minimally rigid is still satisfied, and it's also clear from the construction. And since we have k copies of our original graph, and each one we can somehow move independently to achieve all its realizations, we get a Lamarck number that is the case power of the original Lamarck number. Now, if we change the viewpoint and if we ask for a graph with n vertices, what is the highest Lamarck number that we can achieve, at least? Yes, then we do this construction, and this means we have to divide this number n, and actually n minus 2, we have to divide by v minus 2. So this gives us, if we take the floor, this gives us the number of copies that we can place, and we take the Lamarck number of G. And for the remaining vertices, we can do this construction where we add one vertex after the other and doubling the number of embeddings. This gives us this little factor, but the important thing is here, so that as n goes to infinity, the growth rate is approximately 2.21 to the power n for the number of realizations. And the second construction is the so-called fan construction that works kind of similarly. So we take a graph and we specify a certain triangle in this graph, and then we again place copies of this graph that share this triangle. Okay, again, we can do the count and convince ourselves that everything is fine. Now, here it's a bit different. This triangle can have 2 embeddings. This gives us these 2. And then the remaining embeddings is the Lamarck number of G divided by 2. This is then raised to the power of k. And so in a very similar fashion that I now don't go into detail, we get this formula. And if we consider large n, we get a lower bound that is a bit better than the previous one. So before we had 2.21, now we have 2.289. And by generalizing this construction, so nobody prevents us from restricting us to a triangle here, but we can take a larger minimally rigid graph that is shared among all the graphs that we construct here. So this gives us a so-called generalized fan construction. The formula is completely analogous to the previous one. And we can play this game to get better and better lower bounds. So here, this picture shows the growth rates that we obtained from different such constructions. So we see the red curve is the caterpillar, and we have already seen that using the triangle fan, this is the blue here, for n equals 6, this is the two numbers that we have seen. And if we do this with larger graphs, then we get better and better bounds. And then H1 fan, H2 fan, H3 fan refers to this generalized fan construction where we don't take a triangle, but bigger graphs, like H1 is this minimally rigid graph that consists of two triangles and so on. This H3 is the 3-prism graph. And then, so until 12, we can really, since we have all the graphs and we are able to compute all the Laman numbers, we can say that this is the best that you can achieve when considering 12 vertex graphs. But what is beyond here is shown in a lighter color because this is a bit speculative. This is the best we could found, but since we were not able to do an exhaustive search here, we cannot claim that this is the best possible. And yes, so this is basically all I wanted to say. Thank you very much for your attention. Thank you.
Thank you, Christoph. Can anybody hear me? Because I just changed my microphone. And
yes, I can hear you.
Yeah, thank you very much. I could ask a question, but can anybody first ask their questions? Anybody? Nobody has a question? Okay. Yes.
I have a classical one. You expose a study of 2D rigidity graph, but did you examine 3D or 4D rigidity graph?
Yes. Okay. Yeah. Thank you for the question. Of course, this is a very natural question, in particular also for practical purposes. We are living in a 3D world. So the theoretical result that I showed in the first part, this unfortunately works only in 2D. And it's, of course, we thought about this question, whether this could be generalized or extended to 3D, but there are certain technical obstacles and that at least make this approach impossible to work in 3D. But we did work in 3D. So the picture that you see here, we have produced a similar picture for graphs, minimally rigid graphs in 3D. But for this purpose, we had to go back to the Gröbner basis approach for computing these numbers that actually we call Geiringer numbers, because as I mentioned in my introduction, the name of Geiringer is highly underrepresented in this field. So we thought that she highly deserves also something named after her. And of course, we could by far not go so far with the number of vertices. So we only looked at graphs with very few vertices, maybe up to 10 or something like this, and computed these Geiringer numbers and did a similar study for lower bounds. Of course, then you could go on with higher dimensions. I think we did some experiments in 4D, but yeah, it of course gets more and more computationally expensive.
Okay, thank you.
Any other questions? Okay, then maybe I ask my question. I'm interested in this caterpillar and these other constructions for creating new Laman graphs out of old, or minimally rigid graphs. So my question is it true what I understood, that you can reconstruct all the Laman graphs with maximum number of realization using the caterpillar, using the triangle fan, let's say, construction?
Okay, yeah, that's a very good question. No, so this construction is to get a bound. So to have a witness that if I want to consider graphs with 100 vertices, I can construct a graph which which probably has this many realizations. What I cannot prove, and it's completely infeasible to tell whether this one is actually the one with the highest Lamarck number. Most probably not. But you know, there are so many graphs that you are not able to enumerate them. So this is just to have to in a greedy way to construct a graph with as many as possible realizations. But definitely this will not be the one with 100 vertices with the highest number.
Yeah, but you do have this under 12 vertices. What you know what they are. So from a lower number of vertices, when you do a triangle, can you get these? Although maybe you can, because I mean, if you have this triangle fan, if you have a generalized triangle fan, like say the whole, because from what I understand from the triangle fan construction is that you can generalize it to any subgraph, not only triangles.
Sure, yes, any minimally rigid subgraph.
So trivially you can get it because you can get the graph itself and then
yeah, of course, yeah. But this is of course kind of trivial. Yeah.
All right, so and nothing is known, again, I asked about the real number of maximum real realization on the real plane.
Yeah, okay, good. So as you may have realized that there's one page number missing. So I can quickly answer this question by showing my last slide. That was somehow an outlook about real realizations. Of course, it's also a very natural question to ask for our original motivating setting with the real numbers. And so the answer is that sometimes we can find a labeling that gives us as many real embeddings or real realizations as in the complex world, but not always. So there are concrete examples where one can show that the number of real realizations is strictly lower than this Lamarck number over the complex numbers. And it's another part of this game, this research, to come up with concrete such real realizations. So here you see the three prism graph. So you see the two triangles here that are connected. And so here we found a concrete assignment of edge lengths for this graph such that it has the highest possible number of embeddings, namely 24. And why you see only 12 here is because the other 12 you get by flipping. So you see that this triangle here, this equilateral triangle, always points to the right. Yes, you see. And so by flipping, you get the other 12, you get the 24 real embeddings that you expect.
Okay.
But this is extremely difficult to find these to find these lengths, so that really all the solutions are real. This is a completely different business.
Okay, so unfortunately we are low on time. I have millions of other questions, but we will leave it. We will start maybe at 11:45 because we went a bit late. So yeah, at 11:45 we have a little break and then we start at 11:45. Thank you, Christoph.
Thank you.
Okay, I think we will very shortly begin. The next speakers, I will surely mispronounce all of these names. That is, correct me if I'm wrong, Marinkovic, Sokilovic, and Maric on automating triangle construction in absolute and hyperbolic geometry. You may now start.
Okay, hello everyone. I will today talk about the joint work done with Tijan Žukelović and Filip Maric on automated generation of solutions to triangle construction problems in absolute and hyperbolic geometry. Construction problems in geometry are one of the longest studied problems in mathematical education. The task of a construction problem is to describe a construction of required geometrical object which satisfies the given set of constraints. For instance, we may have to construct the triangle ABC given two internal angles and the length of one side. The solutions to construction problems are not the figures, but the procedures which gives us in a very precise way how to construct the required object. And one of the problems arising when solving this kind of problems is that some instances are unsolvable. So, as we all know, many different geometries exist, and the question of constructability and constructions itself depend on the underlying geometry. So absolute geometry is based on the four groups of axioms. So axioms of incidence, axioms of order, axioms of congruence, and axioms of continuity. And by adding the appropriate axiom of parallelism, we can get either Euclidean geometry or hyperbolic geometry. So if we assume that there is one unique line parallel to a given line A through a point A, then we get Euclidean geometry. However, if we assume that there are infinitely many parallels to a given line A through a given point A, then we get hyperbolic geometry. And this scenario is illustrated here in this figure in the case of a Poincaré disk model, where lines are represented by the circular arcs contained within a disk. So if we take a look at one simple construction problem in Euclidean geometry, where the task is to construct the triangle ABC given one vertex A, then the midpoint of a side BC and the feet of the attitude from the point B, the corresponding construction would be quite easy. So we would construct the line through these 2 points. So this is the line AC, and we would construct the circle centered at point MA passing through this feet of the attitude. And then as the intersection point, we would get one vertex and another also in the easy way. What is the problem here is that some of the facts that we use for generating this construction are not valid in the hyperbolic way. So what's our goal here? It's to automatically find constructions that are valid in absolute geometry and also to automatically find constructions that are valid in hyperbolic geometry. The most commonly studied construction problems are the ones where we have to construct the required object using the straight edge and compass. And the solution to that problem is a sequence of elementary steps where each of the steps is one of the steps listed here. So construction of an arbitrary point, or a line through two given points, or a circle which is centered at one point passing through some another, or a construction of an intersection point of two lines, two circles, or a line and a circle. However, usually we use also so-called compound construction steps, which are consisted from more elementary steps, like the construction of a midpoint of a segment or a perpendicular to a given line through a given point, etc. To be able to automatically solve construction problems, we needed to analyze the solutions existing in the literature and to systematize the knowledge needed for their solving. And based on that knowledge, Predrag Jančić and me, we developed one solver for automated solving of location construction problems. And we then only thought about the constructions in Euclidean geometry. And this solver, we called it Arbitrix. It can automatically export the textual description of a construction and also formal specification of a construction in GCLC language. And Today, I will talk about our work, our effort to adapt this solver so that it can also give us constructions in absolute geometry and hyperbolic geometry. The corpus of problems we worked with is a Wernicke's corpus, which is formulated in 1982. And each of the problems from this Wernicke's list has the same goal. So we have to construct the triangle ABC given the location of 3 out of these 16 significant points illustrated here. So these significant points are 3 vertices of a triangle, then 3 side midpoints, then 3 feet of the internal angle bisectors, 3 feet of attitudes, circumcenter, centroid, incenter, and orthocenter. And in Euclidean case, the status of all problems from this list is found, and some of the problems are proved solvable. Some of the problems are proved unsolvable. Some of the problems are proved redundant, meaning that one of the points given can be constructed using the 2 others. And some of the problems are proved locus dependent, meaning that one of the points given must belong to some locus of points determined by the other 2 points in order for the problem to have a solution. The knowledge we identified was split in 3 sets. These are a set of definitions, set of lemmas, and set of primitive constructions. Let us illustrate this on this problem. So if we take again a look at one problem where the task is to construct triangle ABC, given 2 vertices, A and B, and its centroid G, one possible construction in Euclidean case would be the following one. So we could construct the point MC as the midpoint of this segment, and then we can construct the 3rd vertex C using this fact. We can see that in this solution, we use the following knowledge. And the 2 first items correspond to definitions of significant points. The 3rd one is the lemma, stating that the centroid of a triangle divides the median in the ratio 2:1. And the last 2 are actually primitive construction. How can we construct some object if we are given some others? And our question is how to adapt this solver, Argotrix, so that it can give us the construction in absolute geometry or in hyperbolic geometry. And some portion of knowledge identified is shared. It is valid in hyperbolic case also, but some definitions needs to be changed. Some lemmas need to be changed or adapted. Some primitive constructions needs to be changed. But what's important is that the search algorithm remains the same. So let's take a look at the definitions. We can see that in case of Euclidean geometry, many notions can be defined in different ways. Here we have one example. A median can be defined as the segment that connects a triangle vertex with the midpoint of its opposite side. Okay. But also for median, it holds that it is the segment that divides the triangle area in 2 exact halves. And these 2 notions coincide in the Euclidean case. However, in hyperbolic case, this is not the case. So the first characterization would give the object which we would call median, and the second characterization would give a pseudo-median. And this would be the case for many more objects that are significant when we are considering the triangle. And what can we see is that some theorems that called in Euclidean geometry, like the well-known that centroid, circumcenter, and orthocenter are lying on a so-called Euler line, it holds, but for pseudo objects, not for the regular objects. So here we can see that we can expand our set of significant points of a triangle by adding the regular object like orthocenter and a pseudo object or a pseudo orthocenter. And then we have bigger set of these significant points and a larger set of construction problems we can consider. However, one problem is that some of these pseudo elements are not constructible using ruler and compass. We can also see that some theorems are weaker in absolute geometry than in Euclidean geometry. For instance, in Euclidean geometry, we have that the sum of internal angles of a triangle is always equal to pi. However, in absolute geometry, it can be less or equal to pi. Then centroid and in center of a triangle always exist. However, a circumcenter and orthocenter of a triangle need not exist. Here we have illustrated this for the orthocenter. If we take a look at this first figure, we can see that orthocenter exists since the altitudes intersect in one point, which is lying in the disk. And in these two cases, the triangle would not have an orthocenter since the corresponding line do not intersect in the point in the disk. Here is on the disk and here they do not intersect at all. Then some lemmas that we are familiar with and that we use extensively while solving construction problems in Euclidean geometry do not hold in hyperbolic geometry. For instance, that the centroid divide the median in 2-to-1 ratio, or that the inscribed angle subtended by a diameter is right always. So we need to find some other lemmas to change, to replace these ones in order to solve corresponding construction problems in a hyperbolic case. And some of the lemmas that were added to Argotrix are listed here. Here we have one lemma that is actually true in absolute geometry. So we could have it also in our Euclidean solver, but we didn't need it since it could be replaced by some other lemma, which is more common in case of Euclidean geometry. And the lemma is that if one vertex of a triangle belongs to some line P, then the vertex B belongs to a line which is an image of a line P under the reflection with respect to side midpoint MC. And here we have that also in hyperbolical case. We also had to add some lemmas that are specific for hyperbolic geometry and that could replace the lemmas which is holding in a Euclidean case. And here we changed the notion of parallelism with hyperparallelism. So we have that the midline of a triangle is hyperparallel to a corresponding line, corresponding side of a triangle, and that this point MC is their common perpendicular. We also had to change some primitive constructions since they are not valid in hyperbolic geometry. For instance, we cannot always construct the point Y given point X, Z, and W for which this ratio holds. But we have that some special cases are true. So, and they can be done in hyperbolic geometry, for instance, to construct the midpoint of a segment or to construct the point which is symmetric to one point with respect to another one. We also added primitive constructions related to reflections, since reflections are somehow the basic language of absolute geometry. And we also didn't need them in Euclidean case, since this could be carried out by some other primitive constructions. And here we have one example, which is specific for a hyperbolic geometry. So the task is to construct the triangle ABC given the three side midpoints, MA, MB, and MC. And we can see that we can use newly added primitive constructions that we can construct the line that is hyperparallel to a given line through some point. We considered all the problems from Wernicke's list, and from 139 significantly different problem, we found 31 of them solvable in hyperbolic geometry, and we generated corresponding solutions. And 1 is redundant and 11 locus dependent. The solutions to all problems we managed to solve are given on this web page. So you can go there and take a look later. And to conclude this talk, what we have done, we tried to solve construction problems in absolute and in hyperbolic geometry. For that, we needed to identify which definitions, lemmas, and primitive constructions need to be changed or added in order to have constructions in corresponding framework. We have adapted our solver, Argotrix, for solving constructions, and we managed to solve certain number of problems. That number of problems is not too big, but we strongly believe that constructions in hyperbolic geometry are harder than in Euclidean case. And we think that many problems could be proved not constructible using ruler and compass. Okay.
Thank you, Esna. Very interesting talk. We have time for maybe one question. Is anybody interested in asking? Yes, Pascal?
Yes, I have a lot of questions, in fact, but I just will ask one. The main result in Euclidean RC constructions, I mean, ruler and compass construction, is the one from Galois theory. And I was wondering if you examined an algebraic approach to have such a result in hyperbolic geometry.
We haven't tried algebraic approach, and we haven't found that someone was trying to use algebraic approach for solving constructions in hyperbolic geometry, but that could be interesting. And I know that you have done many things using this algebraic approach, so it could be interesting for work.
Oh, I have other questions. I can ask another one if I'm
well,
asked.
According to Zoltan, you have time for 2 more questions.
Okay. Just an integral one. In the classical geometry, I don't remember the list. I have 139 problems. And what about the number of problems with considering pseudo objects in Wernicke list? Or sorry for my English. The original Wernicke list has 139 problems.
Yes.
Okay, but considering pseudo objects in hyperbolic geometry, I was wondering how problems correspond to Wernicke lists.
We take a look at all problems from Wernicke's list, 139, and we worked with these regular objects, so not with these pseudo objects. And I'm not sure what was the actual question.
If you replace, I don't know, centroid by the notion corresponding to centroid, there are several notions corresponding to centroid. You have more problems.
Yeah.
Okay,
well,
so
we would have.
Is how many?
I'm not sure, since we should calculate how many significantly different are, but we would have orthocenter and pseudo-orthocenter. We would have centroid and pseudo-centroid, and considering points, I think it would be that. But then we have these, as I already said, lines, which are not the elementary objects given in the Wernicke's list as an input object, but are used during the construction. So I think just 2 points more. So not 16/3, but 18/3. And then we have to calculate how many significantly different there are.
Okay, thanks.
Zoltan, you raised your hand. You want to ask a question?
Thanks, just very quickly. Well, let me copy one link or two once in the chat, because I have a friend in Hungary. He is a retired professor, and he is very interested in hyperbolic geometry, and he wrote a book in Hungarian, and more, so the half of it is translated into English, but not everything. And there is one chapter that is related to such things, which constructions are valid in Euclidean geometry and which are also in hyperbolic, and maybe you can have a look. So this is an interactive GeoGebra book, and maybe you find it interesting.
Thank you very much. We would very appreciate this knowledge, because, as I already said, the first step is always done by hand. So analyzing the solutions, seeing what holds, which doesn't hold, how can we, which lemmas new can we discover and add to a system so that it can find some alternative constructions. So this will be of a very big help. Thank you.
Thank you.
Okay, thank you. Thank you for sharing the link, Zoltan. So we will now proceed to the next speakers. I'm not sure who will be representing the next set of speakers. Is it Mr. Zeng? Are you the one? Could you maybe share your presentation screen? So, or do you have the rights? You are muted right now, so maybe I'll. Hello?
Yeah.
Okay.
I'm trying to share the screen of mine and looking for where is the, here. Here is.
Yeah, take your time.
Yes.
No problem.
So then I go to the. So can you see my screen now?
I cannot, but I don't know if the others can. Well, no, I'm not sure. Can the others see the screen?
So I hope.
No, not yet.
Okay. Zoltan says no.
I shared it. So. Or do I need to use PDF style? Maybe it's better for others.
It's a button in the middle lower part. Share screen.
Is it good now?
No, not for me at least.
Yet. Still not. Still not.
You need to select the window or the screen and then click OK again. So it's a two-step.
Okay. Process. I try again. Yeah. So
it seems there's a technical problem.
Yes, no, it said.
Maybe you can send your PDF to us.
Yeah.
Per email,
yes,
and we will.
We will share it.
And we will share it. So
yeah, okay. I tried to send the PDF of mine.
Okay, to my email.
So
for example.
Now how I can send my PDF to you?
I sent you my email address in the chat.
Oh, okay.
And then I will share my screen, and you can.
Okay,
Okay, no problem. there are always some technical glitches.
You don't need to panic. Don't worry about that.
I should do this earlier.
Okay, no problem. For the other speakers, maybe it's safe to send us your PDFs for the same reason in advance. Then we can share them on the webpage of the conference also. And in such cases, we can look at the slides at the same time.
By the way, Zoltan, your hand is still raised. Is it on purpose or?
No, I think it is because of. So this is how Zoom works. This is how Zoom works.
Okay.
Okay.
Actually, in the meantime, we can show your paper. We can open your paper here.
Okay, I'm already sent out PDF of my presentation to Kovacs Zoltan's gmail.com. So
okay, I'm waiting for the file. So I think, now I have it. I have it. I will download it. Very good.
Oh,
I suggest that you say next page every time you want him to flip the page, you know, when you are giving the talk. So Zoltan will just flip the page.
Okay, I will share my screen now. And I think now you are able
so I can see the PDF of mine now. And can I control this file? So now this is the first page of my talk. It's just the name of my talk. I want to solve geometric inequality, which is maximizing the sum of the distances between 4 points on the here. It's a unit hemisphere. Sorry, this is not correct. It's a hemisphere. 4 points on the hemisphere. So I want to go to the next page now. So this is the outline of my talk. So in the first, I give the problem. I will describe the problem shortly, and then I show the main result, and then give some lemmas. Then the fourth step is the automated deduction process. Then finally, I will give 2 open questions related to my talk. So please go to the next page. Thank you. Yes, this is the problem. So you can see if we have 4 points A, B, C, and D on the unit hemisphere here, or also a mistake. It's half of the sphere. It's a hemisphere. We want to find the best configuration of ABCD so that the sum of their mutual distance is maximum. The 2 possible solutions are in first case, we can put 1 point D on the North Pole and the other 3 points on the equator to form one regular triangle. This is the first possible solution. And the second one is you put 4 points, all four points on the equator. Then we will see the in first plane, you have 9.4387, and the second plane is better. So generally people would imagine the first plan is better. So please go to the next page now. And then we also use computer numerical searching to try to find the solution of the similar problem for larger n from 5 to 12. So the results is for n equals to 5, for 5 points, the best numerical solution was you just put the 5 points on the equator so that the 5 points form one regular pentagon. And for n from 6 to 12, we always have the best numerical solution. For you put 1 point at the North Pole position and the other -1 points on the equator. So this page shows just the numerical solutions. So can you go to the next page? Then in this, till now we have only solved the problem for 4 points. The result is for any 4 points, A, B, C, D on the unit hemisphere. Sorry, here is hemisphere. I don't know why I wrote the unit sphere. The sum of their distance is not greater than this number. 4 plus 4 multiply square root of 2. So this is the result we proved. And we also proved up to the congruent transformation. The optimal configuration is formed by these locations. So we show the coordinates in R3, and please go to the next page now. So we need several lemmas. The first lemma is proved by Human, so which says if 4 points form an optimal configuration for the maximum sum, then the center of the hemisphere must be contained in the interior of the convex hull of the 4 points. And therefore, this result would imply that at least 3 of the 4 points lie on the equator of the hemisphere. Actually, this lemma is true for 5 points or 6 points or other cases. And we will shortly show the proof later. And the second lemma we will need is that this is easier to prove. The following 4 points, these special locations form a local maximum configuration of the original problem. This is relatively easy, just use calculus to show that. And please go to the next page. The third lemma, we will use extensively symbolic computation to prove, which says we can construct 3 small neighborhood UVW and prove that for any points B selected from the hemisphere, the intersection of the hemisphere and the U, and the point C from the V intersected with the hemisphere, and the fourth point D in the W, then we will have this inequality. Here, we put A equals to a special point on the hemisphere, which is actually the intersection of the equator and the median of the from North Pole to the to this point. So here we can also see the UVW is explicitly determined with delta 1 equals to 1/32 and delta 2 equals to 1/4, and UVW are determined by delta 1 and delta 2 in this R3. So which is actually very small neighborhoods. In next page, so in this page, we show the first graph. In first picture, we show the projection of the neighborhood on the equator, and the second picture shows roughly the shape of the neighborhoods. So please move to the next page. And the fourth lemma, the final lemma, we will prove. For this, we will use the machine by using numerical search to prove on the other areas, which means if you select B, C, D from other places in the hemisphere, then this inequality is also valid. So this is the fourth lemma. And then we go to the next page. So this gives the sketch of the proof of first lemma. It looks quite tedious, but it mainly contains two steps. So first, you find the shortest line connected with the center of the hemisphere with the convex hull of the 4 points. Then you draw a perpendicular plane with this line. Then you will get a new smaller hemisphere to contain these 4 points. And then we show next page. Then we will find a new sphere which radius is less than one. So then finally we get some contradiction. I think we go to the next page to see further. This is also the part of the proof of lemma 1. And please go to the next page. So this lemma 2 is easier to prove, and the main contents of this talk is the proof of lemma 3. So it's contained how to construct a small neighborhood of the critical points so that all points B, C, D in the neighborhoods will satisfy the inequality. This just repeats the lemma 3. So we go to the next page. And this picture also we have seen already. This just shows the coordinates of the points A, B, C, and D. So we use parameter S, T, U, V to express the points. And we go to the next page to see further things. So thank you. We need to go to the next page. So now in this page, we just represent the distance of between A, B, and C and D to some kind of factions of STUV. And yes, the time is already not much. And then we go to see the next page. Here, because the fraction of the distance sum contains the square root, we need a lemma that was obtained by a kind of Taylor series. And the proof is also very simple. And just go to the next page to see. Then we will use computer algebra to obtain this expression. The sum of the distance is smaller than a number 4 multiplied square root of 2 plus 4 plus another fraction, which denominator is a kind of positive thing. And we will prove that the numerator is also a kind of negative semi-definite polynomial. So this, it contains H2, H3, H4, and please go to next page, C. Then the last thing is H23, H24, which H24 is degree of 24, H23 is degree of 23. And the monomials of these polynomials are listed as these things. And please show the next page. And then we need a kind of estimator to simplify the numerator to this form, H2 plus H3 plus H4. And all others is simple things like this, 4 terms, 4 monomials. And then we go to the next page. Then finally, we changed the numerator J to this form. We will. This is now. It is easy to prove that the matrix is a negative semi-definite. So we finally proved that the numerator is always negative. And then actually we will already, please go to the next page. So actually this lemma 3 is proved in this way. It involves a lot of symbolic computation. We use that in Maple, and then we quickly see other pages. So maybe next page. So this lemma we proved in other place because it takes a lot of pages, and maybe next page. Next page is just the sketch of that lemma. And we use divide and conquer, this kind of way to prove the inequality on that. And also next page. This shows that a little detail of the division of supercube in 7th dimensional space. And please see next page. This is also a record of, in the beginning, we use the cubes of h 1/8. So next step is 1/32. Finally, 1/128 and 1/512. So this red numbers shows the times we used in the computer. And please go to the, this is a solved problem, as we already said, for n equals to 5. We guess the optimal configuration was a regular pentagon on the equator. And also for others, it's still unknown. So we hope in future, other people could find some better way to prove this. So it's already the last page, and please go to the next page. It's thank you for intention, and I'm very sorry for
no problem.
Hurry, and I was not able to share my screen. Thank you for
very interesting talk. Does anyone have any question? I know Zoltan has his hands raised, but I'm not sure if he has a question. So you can unmute if you have anybody. Just say something if you have a question, because I think everybody has the ability to unmute. Otherwise, I have a very small question.
Oh, sorry.
Oh, no, I'm sorry, Pascal. You start.
Oh, okay. I have a question. You use recursive subdivision to solve your problem. I was wondering if your method can also work for another problem consisting in the same problem, but if with a quarter of the unit sphere instead of hemisphere.
Unit sphere for points would be relatively easy, because it's possible to find the very symmetrical locations. But for 5 points on the unit sphere, this would be rather difficult. But for hemisphere, 4 points on hemisphere is already, we tried to find if there are kind of elemental way to prove using hand computational kind of this, but we were not able to find this solution. So maybe for 5 points, maybe if other people try this problem, probably it's possible. There are always good techniques to find, certainly find some good solution to geometric inequality. So.
Okay, thank you.
My short question is the shape of, if for instance for the four points, is it unique, the shape?
Yes, the distance we mean is the Euclidean distance between 2 points. Just you connect the 2 points by line, and we measure the distance. Sorry, in this first page, I wrote unit sphere. This is completely wrong. It's a unit hemisphere.
Okay. All right, thank you. So, so I think this concludes today's morning session. We have a break until 2 p.m. Central European time.
2 p.m.
Yes, and that's roughly in 1.5 hours from now. So, yeah.
Oh, thank you.
Most of us will go probably eat lunch, and we see you in 1.5 hours.
Thank you. I'm sorry, my eyesight not good, so you see the very big face of my.
No problem at all. No.
very close to the screen. Thank you.
Thank you, Zoltan, and see you in 1.5 hours, everybody.
Yeah.
Thank you.
Thank you.
See you
Goodbye.
later.
See you later.